Yeah, we usually think of physics equations as these really rigid rules, right? Things that bring order to the chaos of the universe. But what if some of the most important equations not only describe order, but secretly contain the instructions for creating chaos itself? So that's really our big question today. When we write down a formula for how water flows or how air moves or a wing, we guarantee to get a simple, predictable answer. Well, the story we're about to have for breakfast suggests that the universe answer is surprising and, frankly, a fascinating nope. Well, to really understand how radical this idea is, we need to take a step back and appreciate the classical way of thinking. For centuries, the goal of physics was to find this kind of mathematical perfection. And look, this weren't just nice to haves. Physicists generally believed that the universe had to work this way. Any solution to an equation had to be smooth. No crazy sudden jumps like you see in so many fields. It had to be unique. One starting point leads to one and only one outcome. It needed to be stable, so that a small nudge wouldn't send an entire system into a completely different future. It was this dream of a perfect clockwork universe. Now, for anything that flows, we're talking water, air, you name it. The absolute gold standard for these rules were the Navier Stokes equations. Yes, those famous and famously difficult to solve. And for the longest time, everyone assumed that if you could ever crack them, you'd get the one perfect, unique, smooth answer describing exactly how the fluid moves. But here's the twist. The clue that would completely shatter this perfect little picture didn't come from the stallion fluid. It came from the brilliant and yes, the eccentric mind of the mathematician John Nash, who was thinking about a completely different problem in the super abstract world of geometry. Well, don't worry. Let's not get lost in the jargon here. Think of it like this. Imagine you have a crumbled out piece of paper. The question is, can you lay it perfectly flat on a table without stretching it, tearing it, or creating increases? Nash was essentially asking for a much, much more complicated version of that. But for abstract mathematical shapes, it is a puzzle about fitting and folding. So instead of trying to find one single grand smooth solution to this problem, Nash took a completely different approach. He decided he was only going to build his solution piece by piece. He did so by embracing the imperfections along the way. His method was iterative, meaning you do it over and over. First, you just start with a very poor approximation, which is obviously wrong. Then you figure out how it is wrong, and that's your error. And this is the absolute genius of it, instead of trying to smooth the error out, you got a very fast, very fine wrinkle to correct for it. Then you look at the new smaller error and add an even finer, even faster wrinkle. Then you just keep going over and over. And this is the powerful idea behind it. Each new attempt at your solution is just the old one plus a new little corrective wiggle. The crazy thing is, with each step, your solution doesn't get smoother, but rather more complex, more and more wrinkled. But it's also getting closer and closer to being the right answer. Okay, so this is where story takes a really wild turn. I mean, seriously, how could a technique for folding abstract shapes possibly have anything to do with the chaotic flow of a river or the turbulence you see behind a jet engine? Well, this was the revolutionary leap. So physicists and mathematicians started thinking, wait a second, why don't we just stop trying to force our fluid equations to have the perfect, smooth solutions? What if we take a rough guess, find its error, and then, like Nash did, add a little wrinkle to cancel the error out? Apparently, in fluid dynamics, this error already had a name. Reynolds stress. It's the term in the equations that basically captures up all the messy, turbulent stuff that doesn't fit the nice, clean, smooth picture for the equations. For decades, the goal was to get rid of it, to eliminate it. The new idea was to absorb it instead, embrace it, and this new technique, which we now call convex integration, pretty much turned everything upside down. It wasn't about finding a solution anymore. It was about building one using the very same messiness that physicists had spent years trying to avoid. I mean, this really shows you the total shift in thinking the old way. The classical approach was all about smoothing out any errors to force a single smooth and neat answer. Convex integration just comes in and says, nope, embrace the error. In fact, it uses the messiness as a building block, constructing a totally valid solution by leaning on this controlled, intricate chaos. So here's the mathematical magic trick, right? You got these tiny, super fast wheels on their own that are almost nothing, but it's their interactions, the sum of their parts, the way they can multiply and interfere with each other that creates this combined effect, which is the exact opposite of the earlier time fits. They cancel each other out perfectly, leaving you with a solution that's valid, even if it's incredibly complex. Where does all this lead? To some very, very strange places. To say the least, the final solution you end up with isn't smooth at all. It's infinitely wrinkled. And this is what mathematicians call a weak solution, and this has huge implications for reality. It means that non uniqueness is possible, so multiple completely different flows can come from the same starting point. It allows for crazy amounts of irregularity, and maybe most shocking of all, it opens the door to some truly bizarre behavior with energy. But even this new world of chaos isn't completely lawless. Turns out there are rules, and these rules govern just how wild these solutions are, and this led to one of the most important predictions in modern mathematical physics. One third, this simple little fraction, it turned out to be like a universal speed limit for chaos in floods. A critical line in the sand separates two completely different physical realities. This is called the Onsanger's conjecture. It all boils down to a way of measuring a solution's roughness. And if a solution is relatively smooth, meaning its roughness value is greater than one third, then energy is conserved. Just as we learned in high school physics, everything's fine. But if the solution is rougher than that critical one third threshold, well, that is rough. The flow is so wild that energy simply disappears. And let's be really clear here. This is the mind bending part. We're not talking about energy being lost to heat or friction the normal classical way. This theory predicts that for these incredibly wild solutions, energy can dissipate simply through the complex, almost fractal-like structure of the flow. It literally vanishes into the mathematical wrinkles. So what does all this mean? Well, these ideas, which began with John Nash just thinking about folding shapes, they completely rewrote our understanding of what an equation can even do. It's as if they've opened a door to a whole new mathematical universe. We didn't even know it was there. And this is really the crucial thing to take away from all of this. We thought of the equations as these strict commanders barking orders at the universe, but it turns out they're more like a rulebook for a game that allows for an infinite variety of games. They don't just enforce order, but actually provide the framework for an astonishing amount of complexity and chaos. And that leaves us with one last pretty profound question. For decades, solving the Navier Stokes problem has been this $1 million prize, this hunt for a single perfect solution. But maybe the issue isn't that the equations are too hard. Maybe the problem is that we've been looking for the wrong thing all along. And the true answer doesn't lie in a single solution, but in a whole universe of wild possibilities that we're just now beginning to explore.